This one is a given question of a matrix exponentiation. Um, because we have this one also has a DP solution, which can be considered as a slight brute force approach, but it will not work right now because we have an n of 10 power 15. So the least answer which we can get in terms of n would be at least log n. We cannot get an linear solution, so we need a solution which is a which one would be a log n of the input integers. So the question is we are given n, m, and k. So the question is we are given n, m, and k. So n, I would say, like, this is a very big question, but I would condense this question into a simple format. We have to fill n blanks with m distinct things, which can be anything. The in the given question we have to fill with a to z, and a to z given by the number of numbers they give. But let me assume that we have to fill the blanks with m1 to m. So if we just have to fill the blanks with 1 to m, this one would be a very easy question. But thing is, we don't only have to fill the blanks with 1 to m, we also have to fill the blanks with, I would say, a limitation. So there are k limitations try to, like, stop us from filling a blank in a particular format. For example, let me assume, like, there are some 1 to m can be some 4, so we can fill the blanks with 1 2 3 4, and let there be some from 5 n's. So we have to fill 5 blanks with 1 to 4, and there are the k limitations. K limitations are given in format of pairs. So let me assume a pair can be 2 1 2 3, or I would say 3 1. So what this makes us is that, for example, there is a 2 in the blank, the next blank cannot be filled with 1 or 3. This pattern cannot come, or this particular pair cannot come consecutively. So 2 cannot be filled with 1 as next or 3 as next. And also we can take its reverse. Like, for example, there's a 1, or there's a 1 here and 1 4. Okay, so before 1 there cannot be a 2 or 3, because it makes consecutive pattern, or right, something, etc., etc. And also after 1 there cannot be a 4, right? So I would say it goes forward as well as backward. So there's no particular order. We just don't have to get the particular pattern, and we have to fill the n blanks. So the brute force approach would be, like, firstly, like, filling the first blank with some letters. Then for each letter there is calculated number of ways. Then I would say the next blank is filled. Then the next blank is filled up to some n blanks. It would, I would say, the solution would get a time complexity of m power n, which is very, very big. So dp can reduce the time complexity very much. Dp reduces the time complexity to m star n, because we just have to store dp of I to j, where I would be number of blanks filled, j would be the last term in the, or the ith term in the blank. So I would say the ith term in the ith blanks term. So we have to, like, find dp of I and j. We know that we can convert this into subproblems. So dp of I and j depends on dp of I minus 1 and the last letter of I would say last letter of I minus 1. So what we have to do is, like, we have to check the last letter of I minus 1, and also there is a condition, there is a limitation which we cannot take. So we also have to consider the limitations into consideration. So I would assume, like, I can write dp of I to j, ith blank with j as a last term, which can be sigma of some 1 to m. So dp of I minus 1. Okay, 1 to m each can be considered L, or I would say, yeah, I would say Z. So Z, and also we have to be cautious that whether there is a thing this or not. So for ith term will be as of now J. So here 1 to m is considered, here 1 to m, which would be considered Z, can be considered as before term of J. So we have to check whether there is Zj or not in the limitations. So we have to check kzj. So kzj can be 1 or 0 depending on the limitation. If there is a limitation, it should be 0 because we don't have to add anything from this one, because we cannot go with j from z. So from z we cannot go to j. But if there are no limitations, we can go to j. So it's considered 1. So we'll direct because we'll multiply by 1 and we'll add this one. Also, let me consider this as a graphical approach. We are given m nodes. M nodes. So let me assume that 1 to 2 or 2 to 1 are edges, 3 to 4 are edges. So we are given edges. So we are given pairs, which are limitations. Let me assume that the limitations are nothing but non-edges. So all the pairs given here are not edges. So all types of edges are like all the permutations of edges are possible for the given m nodes except for the limitations. So initially, for example, I would say 3 and 4 are limitation, 1 and 4 are limitation. So I would say except for 3 and 4, there would be every possible edge, like 1 to m, 2 to m, 3 to m, 4 to m, but there would be no 3 to 4 edge. There would be also a 2 to 4 edge. There would also be 1 to 3 edge, but there is no 1 to 4 edge. So this is not possible. So these are the edges format. So what we have to find is, we are starting from a particular edge I. We have to go to a particular edge j in n steps, and each step consists of an edge. So exactly n edges should be traversed to reach j. So number of ways of reaching I to j with exactly n edges. This one is our question. So this one is an incomplete question. What we have to do is like number of ways of reaching 1 to m to 1 to m with exactly n edges or something. So this one is a graphical question. So if you assume as this graph, so we know that we can write the edge matrix for a graph. So we know that if for an edge matrix with, like, for example, there's an edge between some particular to particular, and like where, let me assume like m of ij means like from I to j number of, I would say for basic mij, or for basic edge matrix, for mij number of ways of possible from I to j with only one step, one edge. Let me take an example, 1, 2 and 3. So let me assume that from 1 to 2 there is an edge, 2 to 3 there is an edge, I would say, or there is a 4, 1 to 4 there is an edge, 3 to 4 there is 4 to 3 there is an edge. So m of 1, 3 is firstly number of ways of reaching, I would say, from, let me take this example right now. So number of ways of reaching from here, 1 to 2 is 1, sorry, 1 to 1 is 0, 1 to 2 is 1, 1 to 2 is, 1 to 3 is 0, 1 to 4 is 1. Similarly 2 to 1, 2 to 1 is 1, 2 to 3 is 1, 2 to 4 is 0, 2 to 2 is 0, 2 to 4 is 0, 3 to 2 and 3 to 4 are 1 and 1, 0, 0. Again for 4, 1 and 3 there is a 1, 0, 0. So this one is a number of ways of reaching like from I to j with just one edge possible. one edge route possible. So we need only a single edge between I and j. In the given matrix, the given ones are the only possible edges right now. So let me assume that I need matrix I1 2 3 with exactly two edge route. Like it should traverse the two edges and reach 3. So from the given thing, given example, we can directly find that 1 2 3 is a route, 1 4 3 is a route. But we need a solid computation. So for this computation, we just have to multiply this one. So 1 3 1 3. Let me for the square matrix, m square matrix, the 1 3 would be the first row multiplied by third column. The first row multiplied by third column would be, this is the first row, so for third column the answer would be 2. So here we are getting as 2, which is similar to our approach. So this is just an example. The solid proof would be given in the graphical methods, graphs and etc. So from this we have to understand that we have to draw an edge graph and we have to take it to a power n, and the given vector here would be the initial nodes from which we can start, and also the answer would be the nodes with which we have to end right now. So multiplying to the power of n, where n is 10 power 15, we can get the answer. But the graphical approach cannot provide you a solid solution, solid understanding. So let me dive back into the formula based approach. The formula based approach is this one. So here let I be the same one, but let me change the j. So let me write a vector dp of I 1, dp of I 2 up to dp of I to m. So we need a matrix, and also the answer should be dp of I minus 1 to 1, dp of I minus 1 to 2, and until dp of I minus 1 to m. So the matrix should transform dp of I minus 1 to 1, 2, 3 to m to this particular format. So let me assume the matrix in row format. So matrix in row format can be R1, R2 up to Rm. So what we understand is, like, for dp of I of 1, R1 is multiplied by the total, let me assume this vector as dp of I minus 1. So this vector should be multiplied by dp of I minus 1. So this matrix, this row is multiplied by this vector. So R1 should be such that it converts this thing into this one. So from here you can understand see here j can be 1 to m, which can be possible in the vector, but the only thing which we are scaling this with is kzj. So r can be kzj, and like I would say here the j is constant, so it depends on z. So r can be k1 to j, k2 to j, k3 to j, until km to j. So from here also we can understand we have to use matrix exponentiation. So dp of I vector is dp of I minus 1. So for a single thing we have to multiply by once. For a double transformation we have to multiply twice, I minus 2. So for n things we have to multiply by n with initial dp of 0. So initial dp of 0 is nothing but with where we are starting or where we are going. So initially, from, like, we are starting from 1 to m nodes, so there is definitely a path, like the single blank can end with 1, 2, 3, 4, up to m. So I'll fill each and everything with 1. Here the thing is dp of, I would say, 0 of ending with 1, ending with 2, ending with 3, ending with 4, etc. etc. Sorry, dp of 1 ending with 1, 2, 3, 4, 5. So everything has a chance of 1 because the blank can be filled with 1, 110, 2, 110, m 110. So single blank, so we are getting 1, 1, 1, 1. So we have to take the power of matrix, like get the matrix to the power n. So this one is an exponentiation problem, which takes log n complexity, which can be done very easily. N can be converted to, as in the binary exponentiation, n can be converted into binary format, 1, 0, 1, 0, 1. And for every possible thing, we have to multiply by m power 1 or m power 2, m power 4, and for ith blank, m power 2 power I. And if there is a 0, we have to multiply by 1. If there is a 1, we have to multiply this given number. So we'll definitely get the answer. This one takes a time complexity of, I would say, m square is a matrix size. So since m square is a matrix size, and for each multiplication it would take m cube, like I would say m cube, then we are doing log n multiplications. So the time complexity is m cube log n. So m is very less. M is here 52, or let me assume 100. So the m would be 10. The m cube will be 10 power 6 with the given log of 10 power 15. It will be 15. It does not affect that much. So the complexity does not. The complexity is not that much. The complexity is reduced a lot compared to 10 power 15. So this is the like optimal approach for filling n blanks with limitations. The brute forcing approach, or the I would say totally brute forcing approach, would be the brute force approach with while loops, with for and while loops, which takes power m. A middle approach, or slightly better approach, would be dp, which still takes a lot of complexity because n is very big. So also there is another hint where we can assume that we have to do exponentiation, or we have to do something related to divide and conquer exponentiation when n is very, very large, 10 power 15 or something, etc. So this one is one such problem. I think there are two more problems which I have to do.